Sorry?
YouTube.
Oh, YouTube.
But I think it's kind of linked on my website.
Right.
It's the same where Alcalog.
Yeah. And there is a YouTube channel called Conformal.
Are you also Alberto's student?
No, I'm working with Rachel.
Oh.
No, I usually go
moving, right?
on my
She
own
just
life.
moved to County
Oh, you
Maryland,
were
yeah.
Yeah,
Are you moving with her, or are you going to stay?
No, I'm staying there, so we're working
but
kind of
it's local.
remotely.
Locally.
Going forward. So I'm going to go to County Maryland in the fall.
But when I go
Just to
home,
visit.
You get to
Same thing, yeah.
I have a friend who's just started a faculty position there. He might need research on policy. So, I mean, he's like energy / finance center guy.
no, well, I don't know. At least I don't feel.
Do you feel comfortable?
I feel comfortable.
You did your undergrad at Columbia, right?
I did do undergrad. Yeah, we were just chatting about that. Did you do undergrad at Columbia?
No, I did mine in the UK.
Oh, where are you from?
I'm from Manchester. I did mine in Oxford.
I like Manchester. I visited there for a few weeks.
You visited Manchester.
Oh, that's cool.
Most people don't. Most people just go to London and call it a day, right?
I think Manchester is a really cool city.
Yeah.
I mean, there's a really good music scene.
Yeah, definitely.
The city center is nice. It's small, but like. Yeah. I was there right around. They have some like summer music festival, so the place was like totally packed when I was there.
Okay, cool. When did you go?
When? I forget exactly when. It was sometime during the summer, but it was a number of years ago. Probably like 5 years ago. You might not.
Maybe I missed it last time, but I think from some point on, you kind of switched from like talking about general operators, talking about primary operators, without really defining it and mentioning that.
Oh, well, I did define it. Maybe I was too quick, but at some point I said that the primary is the guy that's filled by the K generator,
Right.
and that unless I specify otherwise, for now on, I'll be talking about primary operators.
Yeah, okay, maybe I missed that. Disclaimer, yeah.
Yeah, I'll do a brief overview. Yeah. Of the results from last time.
By the way, how do you find the Zoom link?
Oh, so I emailed. I've been sending it in the emails. There's it's like a tiny URL which then directs you to
No,
the
I
Zoom
haven't
link.
had any emails about the class.
We haven't got any emails. Have you been getting emails?
No.
Did you email me that you wanted to be in the class?
Yeah.
You haven't been getting emails. Did you check your spam maybe? Did you get the email?
Yes, yes.
Okay.
I got it too.
Has anyone not been getting emails? Okay, so can you guys email me again? And then I'll double check that I put you on the email list. And also check your spam, because it's possible that
Yeah, maybe it's others.
yeah, because I've been sending numerous emails, maybe too many.
Have you been getting emails? No.
Okay, great, yeah. So just email me again and also check your spam. Oh, it is in your spam.
No, it's not.
I don't understand. Oh, okay, good. Oh, okay.
Well,
So
you
just
should check your spam.
sure. Well, I unfortunately have started checking my spam every day, which kind of defeats it being spam, because I started getting emails to my spam, so now I just check it the way I check my regular email.
That's gonna be more entertaining, right? All kind of interesting stuff there.
Yeah, I mean, I certainly get a lot of unusual emails. You know, I still get those Nigerian emails after all these years. It's like I thought that thing ended in the 90s, but like they're still doing it.
Maybe you didn't have to send the first time.
Yeah, I was just surprised. You know, it was like a blast from the past. I didn't realize like they were still trying to be scammed from Nigeria. So wait 5 minutes. I'll wait maybe another minute.
Maybe we should down the space time.
Sorry.
So we should down the space time. Instead of waiting for 5 minutes, now we should wait for 4 minutes, 3 minutes.
Well, okay.
Okay, I think we can start.
So I will just go ahead and start. Won't wait for too long. All right, so thanks everybody for coming for the second lecture in this lecture series. So first I'll just start with a brief recap of the previous lecture. So the previous lecture, the first part was just motivating CFT, and then afterwards we talked about kinematic constraints from conformal symmetry on correlation functions. So what kinematic means is stuff that's just fixed by symmetry as opposed to things that are fixed by kind of dynamics, which is what we're going to discuss today. And so the summary of last lecture is that operators in a CFT are labeled basically by two labels, the scaling dimension delta and the spin L, which is basically the rank of the representation under the rotation group. The scaling dimension is kind of the novelty of a conformal field theory. In a regular quantum field theory, this would not be a conserved quantum number. We also discussed how operators in conformal field theory come in families called multiplets. And so like you can consider the primary, and then a primary generates infinite descendants whose scaling dimension is bigger by integers from the primary, where the primary is basically like the lowest guy in the multiple. We also discussed the constraint of conformal symmetry and correlation functions of operators, and so we showed that the 1-point function is 0, the 2-point function is totally fixed, the 3-point function is fixed in terms of an overall coefficient, and then the 4-point function is kind of the first interesting guy, where it's fixed in terms of a function of two variables, u and v, which are written in terms of the 4 position. So the 4-point function is kind of the first non-trivial guy, and then the last thing we discussed is that because we were talking about a Euclidean CFT, we could just rearrange these operators, and that gave a non-trivial constraint on this function g of u and v. And so I claimed that this non-trivial constraint on this 4-point function will end up allowing us to numerically solve CFTs. And so that will be kind of the main subject of this class. But I didn't say why yet, I just kind of hinted to that. So in today's lecture, unlike the previous one, we're going to talk about some dynamical properties of conformal symmetry. And so in particular, we're going to introduce a quantization, which we did not do in the previous lecture. Okay, so first of all, let's review what we mean by quantization. So for any quantum theory in d dimensions, you have states which are defined along some spatial slice, and then you can define a time direction such that each state is moving through time. And so time is kind of like one-dimensional, it's a single label, whereas the slices are multi-dimensional, if you're considering some quantum field theory in d dimensions. So these slices are living in d-1 dimensions, and this time, of course, is just one-dimensional. And so then in a quantum field theory, you then take expectation values of states on different slices. And then you define your Hilbert space by some kind of evolution operator u, which is defined in terms of what you call the time, which then moves your states through time. And so from these basic definitions of quantum field theory and quantum mechanics, you see that states and operators are very different, because a state is defined all along d-1 directions, this entire slice, whereas an operator is always just defined at a specific point. And so they're very different quantities, for a general quantum field. Now, time, when I say time here, I'm talking about a very abstract time. So you can kind of choose time to be whatever you want. And so in conventional relativistic quantum field theory, if you're just working on like RD, you might as well just choose time to be one of the directions. And so if it was Lorentzian space, you would choose it to be the time direction. If it was Euclidean space, you could choose it to be any of the directions. And then you would just define the slices to be all the directions orthogonal to that special direction you have chosen. In more detail, so if we were talking about Lorentzian space, with metric, R1 comma d-1, so in this case, the time evolution operator u would be e to the I p0, where p is the generator of time translations, and we have an I to this Lorentzian space. And then we would label states by their eigenvalue under the momentum p. And so a state would be labeled by k, which is the momentum, which is what we get when we act with this momentum generator. So the states are living along, all the directions except for the time direction. And then we can time order correlation functions such that all expectation values are now finite. Now, in principle, we could have chosen like a different quantization even for generic relativistic quantum field theory. It's just usually it's useful to choose a quantization such that your time direction respects as many symmetries of the problem as possible. So that just makes life easier. But this was for general quantum field theories. for scale invariant quantum field theories, we have a bigger symmetry group, and so now we are going to choose our time direction to respect that bigger symmetry group. And so, if you have a scale invariant theory, you can now think of slices as, say, like concentric circles, or really concentric spheres. So these are spheres SD minus 1. And then you could think of the radial direction as the thing that's moving you from one sphere to another sphere. And this kind of naturally respects the scale invariance, because scale invariance relates this one sphere to another sphere, by rescaling. And so in this case, instead of your time direction being generated by the time generator, or the conventional Lorentzian time generator, now dilations are the generator that's moving you along. So because we're working Euclidean space, I won't put the I. And so the thing which is moving you along, moving your states, is now e to the d, where d is the dilation generator, which we discussed in the previous lecture. So just as a reminder, this dilation generator was defined in the previous lecture such that when it acts on an operator, it gives the scaling dimension of that operator. This is a state, because I haven't yet. So when the dilation operator acts on a state labeled by delta, then it gives a scaling dimension times that state. Similarly, because dilations and rotations mutually commute, as we discussed in the previous lecture, you can also label states by how they transform under M, which is the generator of spatial rotations. And so similarly, there's some matrix S mu nu, which you get after acting with this rotation generator, some generic spinning state. So for instance, we can define the vacuum as the guy which is annihilated by the scaling generator, by the dilation operator. And so that's the simplest state. It's a scalar state. And so what is one reason why we choose our quantization to be radial quantization instead of the more conventional, time quantization? So the reason is because this makes it clear that you can identify states with operators in a conformal field theory. Now, the fact that you can identify states with operators is a very surprising thing. Because I said just a moment ago, in a generic relativistic quantum field theory, states and operators are very different. The states living on an entire slice and operators just have one point. But what's special about a scale invariant theory is that you can take a state which is living along this entire slice and you can just use scale invariance to bring it to a point. And so that's why, states can always just be identified with operators at one point. Yes?
In principle, that can be done in general serial, just the Hamiltonian dilatation will be time dependent, right? So
So I mean, this just makes it particularly easy to see.
but this identification, it's not special to CFT, is that correct?
No. The fact you can identify states with operators is special to scale invariant theories. You can't do that in a relativistic theory.
You can still do radial quantization and you have time dependent Hamiltonian.
But how do you define the state?
Well, in the same way, because there's only difference is that dilatation
you
now.
have time dependent dilatation.
So you have time dependent Hamiltonians. There are systems with time dependent Hamiltonians. So it may be not very convenient one to work, but state operator correspondence.
It means that at radius 0, roughly speaking, the operator
you can still kind of evolve to infinite past, right?
I mean, I'm not sure that
I did want to make a general comment. There's something known as Krylov subspace methods, which maybe you've heard about, which is a way to work in a superspace where the operators are states actually. It would quite benefit for this.
Okay, so you're saying maybe you could try to relate states to operators at the cost of making your Hamiltonian time dependent?
Right.
Okay, it's possible you could do that, at least for most conventional quantum field theory methods. I think that would make life very difficult. But I think it's only in a scale invariant theory that you can have a conventional time independent Hamiltonian while nonetheless having one-to-one correspondence between states and operators. I'm also not even sure if the correspondence would be one-to-one, but I mean, I guess you're just saying that you could always just you could always just transform it to the center, and then it would just make the Hamiltonian very ugly. Okay, in any event, if you want a standard Hamiltonian, time independent, then you need a scale invariant quantum field theory in order to have a one-to-one correspondence between states and operators. And so then basically for every state which I defined here, it just corresponds to the operator acting on the vacuum. And so this is how you identify states with operators in this scale invariant field theory. And so this is kind of the first, powerful property, we learned from quantization for scale invariant field theory, where we noticed that we haven't used conformal symmetry yet. This was all just scaling symmetry. So another thing we can do now that we've discussed a given quantization scheme is that we can discuss how we define the conjugation of operators. So for instance, if we were considering a standard unitary Lorentzian quantum field theory, so without scaling symmetry, then, as I just discussed, you could have your standard generator of time, which is e to the IP0, and you expect that, these unitary time transformations should preserve the positivity of correlation functions. So in particular, say we take some scalar operator phi, we define it at some position, at some time t and some position x. And so just as usual, the way we get this from an operator at the origin is we conjugate it with the generators of time as well as spatial translations, where we have these signs because we are working in Lorentzian signature for this example. Great. And so we now see that when you conjugate, the left-hand side is Hermitian, so it's conjugating. The right-hand side both changes the sign of I as well as reverses the order of the operators. And so this is what you expect, is that hermiticity should be preserved by time translations. It's an important property of quantum mechanics. So this was in Lorentzian. So I should write this Rd minus 1, comma 1. So now let's say we Wick rotate to Euclidean space. And so we want to learn how is conjugation defined in Euclidean space. And so we basically start with how it's defined in Lorentzian space and just translate everything to Euclidean space. So as usual, when you go to Euclidean space, you define Euclidean time to be minus I times the Lorentzian time. And then you define the Euclidean operator at the Euclidean time and the usual spatial dimension to be the Lorentzian operator at minus I TE and the usual spatial direction. And so if we just plug in these definitions into this, so then we get kind of the analogous formula. So I just put these E's here, and then I get, there's supposed to be a T I forgot before. Okay, so there's TE, this stays the same, and then here you have TE. And so, and then this should also be clear. And so what you see is that conventional conjugation in Lorentzian time in Euclidean space means that phi e of TE x conjugated gives the Euclidean operator where you just put a minus sign next to the time direction. And so, what I've said in some sense is kind of trivial. I was just kind of showing it laboriously, which is that because you've kind of taken away the I by hand, thus, if you want to retain the usual conjugation, you just have to declare that upon conjugating, you put a minus sign wherever this Euclidean time appears. And so this is the case for scalar operators, and there's a very straightforward generalization to spinning operators. And so there's in fact a theorem called the Osterwalder-Schrader theorem, which states that the fact that conventional positivity under conjugation in Lorentzian space is what we call reflection positivity in Euclidean space. And so there's a theorem by Osterwalder and Schrader which says that any reflection positive Euclidean quantum field theory can always be analytically continued in this way to a Lorentzian quantum field theory which is unitary under some very mild assumptions. And so this is like one of the big results of mathematical physics. If you want to look at the proof, I've actually never looked at it, but it's true. And so one immediate implication of this fact is that we can show that OPE coefficients obey certain reality conditions. So recall that in a conformal field theory, a three-point function, which for the moment we're just going to talk about in Lorentzian quantum field theory. So this is one of the rare moments where we actually use Lorentzian quantum field theory. So say we have some operator A, another operator B, these are both scalars, as well as some spinning operator with scaling dimension delta and spin L. Okay, so we have this three-point function, and let's work in the case that everything is space-like separated. So the differences between all operators is the magnitude is bigger than 0. So in that case, these three operators commute. And so recall in the previous lecture that we said in a conformal field theory, this thing is always proportional to some number, lambda, which we can label, say, like A, B, corresponds to these three operators. And so lambda is something like dynamical quantity. It's called an OP coefficient, whose name I'll motivate in a moment. And it's one of the things you're trying to determine in a conformal field. It's analogous like a scaling dimension. It's like a non-trivial quantity you're trying to compute. And so if we apply conjugation to this 3-point function, because all the operators commute, you basically get back the exact same thing you had on the left-hand side. And in order for that to be true, it implies that this OP coefficient must be real. And this is something which will be important in the bootstrap, as we discuss in the next couple lectures. And this is something which directly follows in a unitary Lorentzian quantum field theory, equivalently a reflection positive Euclidean quantum field theory. This would be violated for some generic field theory which does not have unitary. And of course, such field theories exist. I mean, in condensed matter, there's something called like the Yang-Lee field theory, which people studying in 2 dimensions. That is not a unitary field theory, and you don't have this property. So this is really something special, which you only have for unitary field theories, which is the primary subject of this course. Okay, so this is some lesson we can already learn from conjugation, just using conventional quantization, like not having to use our radial quantization. But there's more that we can learn by considering conjugation in radial quantization. And so in order to discuss how conjugation works in our funny radial quantization, as opposed to regular time quantization, we do a trick. So we take our field theory, which is originally Euclidean field theory on RD, and we're going to transform it to a field theory on R cross SD minus 1 by something which is called a Weil rescaling. Weil rescalings are things that don't change angles, and thus they are an example of a conformal transformation. So in particular, we're going to take our metric on RD, which is just the standard metric on RD, which we can write in many different ways, and I'm going to write it in cylindrical coordinates. So this is the standard cylindrical coordinates for flat spacetime.
Conformal transformations are Weil transformations, but not every Weil transformation.
This is true. This is true. Yeah. But I won't be talking about Weil transformations that are not. Okay, so here I've just written down the metric in flat space in cylindrical coordinates. Next step, I'm just going to take out this overall factor of radius squared. And then finally, I do the Weil transformation, which is, okay, well, sorry, I don't do the Weil transformation just yet. And then I do a change of coordinates where I change R to be e to the tau, such that you get e to the 2 tau out here. And then this dr squared over r squared becomes d tau squared. So I'm just doing a change of variables whose motivation will be apparent in a moment. And so this thing, by definition, is just e to the 2 tau multiplying the standard metric on r cross SD minus 1. Because this is r, and this is SD minus 1. So basically, all I did is I just take out kind of the r squared factor, and I redefine it to look like e to the tau instead of being r. And so this has some immediate implications. So first of all, on RD, we defined dilations to make the radial direction become lambda times the radial direction, right? I mean, that's what a dilation does, you know, it kind of changes the radius. If we now think about how that works in tau variables, or, you know, remember r equals e to the tau, so just, this thing just shifts tau by constant. And so we can see that dilations on RD are the same thing as translations on this other space, on the cylinder. And so that means that we can just use standard time quantization on the cylinder, and that will teach us about radial quantization on flat space, which is the thing we ultimately want to learn about. So the main thing we care about is flat space, and we're using this auxiliary space as kind of a tool to learn about flat space. Here I showed how the metric changes when you're going from flat space to the cylinder. But of course, correlation functions change as well. And so you can show that a correlation function of general operators as defined in a certain metric G, say the flat metric, if you go to a different metric, you get these factors omega, 1 for each point, to the power of the scaling dimension. And this is something which just follows from the previous lecture about how conformal transformations affect correlation functions. And so we get the same correlation function, but now on this other metric, which is related by this omega squared. And so this is the metric which is related by this while rescaling, i.e. this omega squared, to the original metric. And so we can now, using this property.
Shai, how does it follow from the previous lecture?
Well, because in the previous lectures we described how conformal transformations act on correlation functions.
Yeah, but conformal transformations are not good.
Okay, but this is okay, we're talking about while transformations that are conformal transformations.
So here you really think about this omega is associated with some conformal
Yes.
transformation.
Yeah, so I'm talking about a while transformation, which is a conformal transformation. Because, of course, the cylinder is conformally related to flat space. I mean, all you're doing is multiplying by this overall factor. Okay, so let's define an operator on this cylindrical space, which we'll call cylinder operators. And so we'll denote cylinder operators just by having the variables in the cylindrical space, so the tau defined here, and then this n, which is a unit vector on SD minus 1. So this thing is just defined to be e to the delta tau times our standard operators. Where in the standard operator, remember that the position is e to the tau times this unit vector. And so the motivation for defining these cylindrical operators with this factor is basically because when you transform correlation functions, you get these factors of omega to the delta for all the different deltas coming outside. Okay, and so now let's ask how conjugation works for these cylindrical operators. So because on the cylindrical space, dilations just became translations. Therefore, if we have standard just time quantization on the cylindrical space, we have the standard conjugation, which is the thing we just discussed before. And the standard Euclidean quantization is, just to review, it's just that if you take some Euclidean operator and you conjugate, you just get the same operator, just putting a minus sign next to the time direction, which is what we call tau. So this is what conjugation is on the cylindrical space. But now, because we can relate these cylinder operators to operators on the flat space, so just using this relation, we can now see how this works on flat space. And so on flat space,
You're cheating here, right? Because cylinder is not related by just conformal transformation to flat space, right?
yeah.
By change of, no, because one has
because
curvature,
it's related by an overall factor.
right, but that factor. So there is a conformal anomaly there, right? Which you're kind of the while anomaly.
Yeah, but there is a while anomaly. It doesn't affect this argument.
Well, it doesn't affect it, but
Yes,
but you're cheating.
you should have taken care of that.
Sure, but I mean, it doesn't, like, everything I've said is correct. So it doesn't affect this argument.
But it doesn't follow from previous class, really.
Yes.
So it's not situation covered in the previous class. You're not just doing conformal transformation.
Yes. It's also Taylor scaling.
Sure. Okay. So maybe I'm cheating a little bit, but nonetheless, I mean, if you assume this relation of how correlation functions change under while rescaling, then this all follows. Okay. So based on how conjugation works on the cylinder, based on this relation between operators in the cylinder and operators on flat space, we see that conjugation on flat space works as follows. This is like our position, and then you divide by the magnitude squared. Okay, and so what are we finding on the right-hand side? This is an inversion, because you're taking the space-time point and you're dividing by its magnitude squared. And so basically what we've learned is that in radial quantization, conjugation is the same thing as inversion. And so what that implies is that, recall from the previous class that we had 4 different space-time generators for conformal symmetry. We have translations, we have rotations, we have dilations, and we had this last thing I called a special conformal transformation. The special conformal transformation was an inversion, and then a translation, and then an inversion. And so because we've learned that an inversion is the same thing as conjugation, and so this is what was generated by this generator K for the special conformal transformation. So what we've learned is that the special conformal generator is conjugate to the translation generator, because inversion is the same thing as conjugation. So in particular, we have learned that K conjugate mu is the same thing as P mu, where P is the generator of translations and K is the generator of the special conformal transformation. And so this is a non-trivial fact which we learned by defining a quantization and using the fact that we can go from the cylinder to flat space because they are conformally related. So yeah, and I actually specified in my notes that this is true even though there could be Weil anomalies in even dimensions. I mean, in odd dimensions you don't have to worry about Weil anomalies. In even dimensions, Weil anomalies do not affect this fact. Okay, so this is another important fact we've learned from quantization. So we've learned two important facts in quantization so far. The first fact is that OP coefficients can be chosen in a basis such that they are real, i.e. coefficients of three-point functions. And the second fact we've learned is that you can choose a basis such that the conjugate of the generator of these special conformal transformations, i.e. inversions, is the same thing as the generator of translations. So now we're going to use this fact to derive some dynamical implications about conformal field theories. Dynamical in the sense that we needed a quantization in order to understand these things. Okay, so in particular, we're going to derive bounds on scaling dimensions.
Another simple question. So you were
Sure.
saying then CFT operators are like states.
Yes.
So what's the size of the Hilbert space?
What's this? Well, it's an infinite dimensional Hilbert space.
It's always interdimensional.
Yeah.
It's not, but because they have infinite number of
Yeah,
operators.
yeah, because I mean, you have operators, for every spin, and also spin is an integer, and then also for every scaling dimension, and the scaling dimension is a real number. So it's a hugely infinite space. Like most, relativistic quantity fields. Okay, but the scaling dimension is bounded, as we're about to learn. So let's consider an operator, or alternatively a state, because they're the same thing, and let's normalize this operator. We give it some label A, because in principle it could be a spinning operator. So this is some kind of general spin label. And let's normalize it such that if you take the 2-point function, you just get a delta function. So that's just a convenient choice of normalization. And so we're going to assume that this operator is transforming in some representation of the rotation group, which is SOD. So it's a spinning operator in general. And so first we start with the trivial statement that a norm is positive. Because a well-defined conjugation, it better give positive norm. And so we're going to start with the following norm, which is P acting on our operator. So this thing is positive by definition. So let's unpack what this is. So this is the generator P acting on this operator labeled by B. And then we can have another generator U acting on operator labeled by A, conjugate. And so, firstly, we can use the fact that K conjugate is the same as P to write this as the state OA, K mu, P nu, the state OB. Where here, I'm also assuming this is a primary operator, or alternatively a primary state, because those are states that are killed by K, as we discussed in the previous lecture. So because these states are killed by K, that means instead of just having K times P, we can actually upgrade this to be the commutator of K and P. And so now we use the algebra, which we discussed in the previous lecture, just to evaluate what this is. And what this is basically a dilation generator as well as a space-time rotation generator. And those acting on these operators using this normalization give 2 delta mu nu, delta AB, minus 2, and then this is the matrix you get from the rotation generator acting on the state. And so we've learned that this quantity must be positive. So the next step is a bit technical, so I won't go into the details. But basically, you want to find the maximum eigenvalues of this matrix, which corresponds to the representation under the rotation group for this specific operator. So when the dust settles, what you learn is that delta, which is what we have here, is greater than or equal to L plus D minus 2, where L is the spin. L is the spin of the operator, and in particular, this holds when the spin is greater than 0. So basically, you just look at the maximum eigenvalues of this matrix, and the fact that this minus that must be greater than 0 implies that the scaling dimension has to be bigger than the spin. And there's also this factor d for the space-time dimension. And so this is called a unitarity bound, because we derived it by choosing a certain quantization and assuming the theory was unitary. So the fact that this norm was positive. So this is a bound which was derived for spin bigger than 0, and we derived this bound just by considering the first descendant of a primary, because all we have to do is act with p on the primary. If you want to consider the case where the spin is 0, so in that case you actually have to work a little bit harder. So you have to consider the second descendant of the operator and then demand that this thing be positive, the magnitude squared of this. And when you do the same derivation, which is in the assignments, for those who are dutifully doing the assignments, you get an analogous bound, which is delta greater than or equal to d minus 2 over 2. So basically it differs by the fact that there's this factor of half here. The only exception to these bounds is the unit operator. So the unit operator is the operator which has delta equals 0 and spin equals 0. So of course this violates the bounds. The unit operator is a bit trivial. I mean, the unit operator is what corresponds to the vacuum state. And so these bounds apply to all spinning operators. Now, I should give a slight caveat. I'm not talking about spin half operators in this lecture. So this is for integer spin operators. I'm not talking about fermionic operators. They would obey a slightly different bound, which could be derived in an analogous way. Of course, depending on the value of d, there could be more complicated representations of the rotation group. So it is not the case that all representations of the rotation group are just rank L representations, which is what I'm calling spin L. I mean, as we discussed in the previous lecture, for instance, in 4 dimensions, you label the rotations by 2 labels, and so you can have things like field strengths, which are 1 forms, etc. And those also obey different unitarity bounds. But for the most vanilla case, which will be sufficient to study everything in these lectures, we just consider rank L representations, and they obey these bounds.
Sorry, in this argument, where did it matter? Was it integer spin or integer spin?
Well, I mean, it's just how the generator acts. So, I mean, and also it's like here when you're going to be finding the maximum eigenvalues of this generator of the rotation group.
So, what will change?
Well, okay, so like, I mean, when you go from here to here, so I mean, this is a non-trivial step.
Right.
So I didn't go through all the details because it's a bit tedious.
So it's
basically, yeah, you have to find the maximum eigenvalues of this matrix that corresponds to the spin group. And so like for all integer spins, it works in the exact same way and you get this value. For half integer spins, it works a little bit differently, and you end up getting a slightly different value. But like morally, it works exactly the same way. That's why I'm not going into detail for these other cases, because I'm just trying to give kind of the general idea. And so you could ask, do you get more constraints by demanding positivity of further descendants? What happens if we acted with PQ, P to the 4? Turns out no. So it turns out like all the constraints of demanding positivity are completely captured just by looking at the first descendant for spin bigger than 0 and the second descendant for spin 0. Great. Okay, so we have these bounds. So the first question you should always ask whenever you're given a bound is what happens when you saturate the bound? Is there something special which happens in that case? And so indeed, there is. This one. So when you saturate the bound, let's first talk about the case when spin is 0. So for spin 0, when you saturate the bound, you're saying that delta equals d minus 2 over 2. And so this might ring a bell for those who were in the last lecture. Remember that d minus 2 over 2 is the scaling dimension of a free field. So remember we wrote down an action for a free field. And we said that if you demand that like the dimension of the action is d and the dimension of a derivative is 1, then this implies that the dimension of phi is d minus 2 over 2. And so this is no coincidence, because when you saturate the unitarity bound for a scalar operator, this basically implies that there must be a free theory. And so it implies not only that you have one operator, which has the dimension of a free field, but in fact the whole theory is a free theory. Now, a slight caveat is that, like, say you have some theory, you could have a theory which is a product of other theories. And so then it could be a product of a free theory and a non-free theory. But assuming there's a unique stress tensor, i.e. there's just one theory, if you saturate this unitarity bound, then it's a free theory. And what's nice is that also, I mean, when you are saturating this bound, you are also saying that p, because like you derive this bound by asking how p squared acting on the operator, how it is related to 0. So if it saturates the bound, that means that p squared acting on the operator is 0, and p is just the generator of translations, which remember is just derivatives. So basically we're saying that you have this differential equation. And this is none other than the Klein-Gordon equation, which is as usual, what you expect to have for a free field theory. And so this is kind of like the first example of a general theme in this class about how we can find that things which you previously learned from Lagrangians are actually just kind of general axiomatic facts about conformal field theory, and you don't need the Lagrangian to learn about that. So here we have the Klein-Gordon equation, and we didn't derive this for some Lagrangian by doing like Netter's procedure. Instead, it just follows from a purely axiomatic approach. Just if you have an operator which saturates unitary bound, thus it obeys the Klein-Gordon equation. So this is kind of like a nice way to kind of maybe bring you back to stuff you might be familiar with.
So you're saying that if we have such an operator in theory, that CFT gets decoupled product of this free.
Assuming there's multiple stress tensors, there has to be at least one sector which is a free theory.
Okay, moments.
Okay, great. And so now, so this was for spin 0. You could do the same thing for spin bigger than 0. And so now let's assume that your scaling dimension is d minus 2 plus L, which was the unitary bound for spinning operators. So in that case, the theory also has to be free. And sorry, I take that back. So in this case, this operator must be a conserved current, because the same way that p squared acting on the operator was 0, in this case we're saying that p mu acting on the operator is 0, and just converting this into a derivative, we're just saying that the derivative, so let's put in some index, is 0. And so this is a definition of an operator being conserved. And so the fact that you have conserved operators does not necessarily imply you're a free theory. Because, so for instance, by definition, a local quantum field theory is a theory which has a stress tensor, T mu nu. And so T mu nu is always conserved, which means that if you act with the derivative, it's 0. And so this is a spin 2 operator. And so all local quantum field theories and all local conformal field theories have a spin 2 conserved operator called the stress tensor. Similarly, if you have a theory which has some kind of global symmetry, then you're going to have a current associated with that global symmetry. So usually that's written as J mu. And again, this is conserved. And so if you have a spin 1 guy, then that means you have some global symmetry. And so these are operators which are kind of guaranteed to exist in any conformal field theory which has continuous global symmetry, or just any local quantum field theory. But now you could ask, what happens if spin is bigger than 2? Like, what happens if we find that we have a conserved current of spin bigger than 2? So this is actually a very non-trivial question, which was settled roughly 15 years ago, and it was proven under some mild assumptions that any theory with a conserved current of spin 3 or bigger must be a free theory. And so kind of like the fun stops at spin 3. And so the only conserved currents we can have are spin 2 or a spin 1. Otherwise, it's forced to be a free theory. Analogous to like when the spin 0 unitary bound was saturated.
Is it Pontus-Zhiboyedov?
Pontus-Zhiboyedov, I think they did it in like 4 dimensions, and then there's also Diab and Alba, who generalized other cases. And there's many various generalizations of this, but yeah, and it's a very non-trivial fact. Like
D larger than 2, right?
In D larger than 2, yes. So I should specify these lectures in general are talking about D larger than 2. The conformal group in D equals 2 is kind of a different beast, because it's a much bigger group. It's a Virasor group. You can have all kinds of like weird exceptions. You can have like interesting interacting theories with conserved currents bigger than 2. Yeah, but we're only talking about D bigger than 2. Okay, so I used the word local, and so this is actually kind of a curious fact, which is that for conformal field theory, we don't actually need to talk about local field theories. So in particular, we can consider conformal field theories which don't have a stress tensor. Or alternatively, we can consider field theories which have a global symmetry, but don't have a conserved current. And it turns out that those theories will satisfy all the axioms of conformal field theory, which we will be discussing in this class, and the only thing they violate is that they just don't have this operator. But everything else works. So you can take correlation functions, you can discuss the 4-point function, and in particular, you can do the bootstrap. And this is of practical importance, because once we get to the numerical bootstrapping part, these non-local theories can appear in our bootstrap plots, because nothing about the axioms of conformal symmetry kills them.
Is having the stress tensor sufficient condition for locality?
Yes. Yeah. In some sense, it's kind of the definition of locality. Because if you have a stress tensor, then you could define the generators of the conformal group as follows. So here I take an integral over some surface which surrounds these operators. This is the generator of the transformation for the generator Q. And so if you just integrate the stress tensor, This will give you all the generators. So this Q could be the dilation D, it could be the translation P, it could be the SCTK, and it could be the rotation generator N. And so this is what's called a local theory, because you're defining this as an integral of this stress tensor. Now, but to emphasize, you can also have the generators D, K, mu, and P, even for a non-local theory. It just means that you're not defining them as an integral of some operator. But you can still define them abstractly. And that's why the rest of the axioms of conformal theory hold, and that's why the bootstrap bounds hold to these non-local theories.
So you mean you just define Q without defining what is T mu?
Exactly, yeah. So I mean, it just defines the algebra in the previous lecture. This is just a way of realizing that algebra in terms of an integral of local operator.
So there is an examples, for instance, when you have this topological operator.
Well, okay, but I can give you a much simpler example. So the simplest example of a non-local conformal field theory is what's called a generalized free field theory. A generalized free field theory is you take some operator phi, you define the dimension of phi to be bigger than d minus 2 over 2, so that it's not a conventional free theory, but then you demand that all correlation functions of this phi can be computed using Wick contractions. So basically, they all just factorize into 2-point functions. And so you can do this, and it turns out this is a consistent thing to do. And then using this, you can define all correlation functions in the theory just by breaking them down in terms of 2-point functions. But you will learn that this generalized free field theory, called GFFT, does not have a stress tensor. And in case you had many different fields, it also wouldn't have a current.
So people know an example where they have the same property, but for the SP1 current.
Yeah, I mean, yeah, because you can also have a generalized free field theory transforming under some rotation group, at ON or something like that. Now, sorry.
Defect conformity too.
Yeah, the defect conformal field theory is another example. Yeah, so this is kind of a trivial example where it's non-interacting. You can also have interacting examples, with defects. There are many such examples. Okay, so one thing you can do in the case of a local conformal field theory, i.e. theories that have these operators, the stress tensor and the current, is that there are kind of general facts you can learn about these operators.
Can I ask you another
Yeah,
question?
sure.
So about this example that you just gave,
Yeah.
Is there some application in the sense that does it show up as a continuum limit of some lattice model or something?
Generalized free field theories?
Yes.
So one example which is of interest to high energy theory people is that when you're studying ADS CFT, which is where you have some quantum gravity, which is dual to the bulk, and so in the limit where Newton's constant goes to 0, so where you basically turn off gravity, then you're dual to a generalized free field theory, which is basically an almost trivial conformal field theory. And so that's one context in which it shows up.
But there are no condensed matter.
And a condensed matter, it would probably show up as well. I mean, okay, I guess defect CFT is not a generalized free field theory. Nonetheless, it's a non-local conformal field theory, and that certainly has condensed matter applications. For just kind of like vanilla generalized free field theories, I'm sure there must be condensed matter applications. I mean, I can't think of one offhand.
There was some Ising model with not nearest neighbor. Some
Okay.
Long range.
But the long range model I think is an interacting theory. I don't think it's a generalized free field theory.
I think it depends on the
I think for some choice,
It probably depends on the coefficient. Yeah. So there's probably some version of the long range Ising model such that it would just be a generalized free field theory.
So it would be helpful if you could just also in your notes just point us to these kind of connections, if possible.
Oh, you're saying between generalized free field theories and condensed matter?
No, I mean you are sending notes around, right?
Yeah.
At some point. So if you could just mention some connections like this.
Oh, sure. Yeah. Okay. So the connections between condensed matter and conformal field theory. So that's discussed.
No, like for
in the
example,
notes.
this one.
Oh, you're saying, but of
Like
non-local
the
field
exotic
theories?
times. Yes. It would be nice.
Sure. Okay. Yeah. I mean, I can mention that as well. Okay. So for local conformal field theories, which have these operators, conformal symmetry has some implications about their CFT data. So in particular, if we study a 3-point function of 2 scalar operators, which I denote by phi, as well as the stress tensor. So as usual for any conformal field theory, we expect this thing to be proportional to this thing called lambda, labeled by phi, and t. And so, this is some, quantity you're trying to compute. And so you can use this equation to prove that this OP coefficient, lambda, is related to another quantity, which is just the 2-point function of the canonically normalized stress tensor. So this guy, okay, so when we spoke about 2-point function in the previous lecture, I said you can always just normalize the operator such as the 2-point function just, is proportional to unity. So you can always do that. But for conserved currents, there's kind of a canonical definition. So it's like when you first learn about the stress tensor, there's some canonical definition, like say you have some Lagrangian, it's written in certain derivatives of the Lagrangian. So with that canonical definition, its 2-point function is not just proportional to the unity, it's proportional to some non-trivial number. So in particular, it's proportional to something called CT, where CT is some non-trivial thing you have to kind of study for the theory. Now, of course, you can always just renormalize T by square root of CT such that it then has unit normalization, which is the normalization we usually use in this class. And so upon doing that renormalization, so let's define like T bar, just to have unit normalization. And so that basically just moves CT, into every other correlation function, which would have had T. And so you can then use this relation, the fact that generators are written as the integral of the stress tensor, to prove that this 3-point function coefficient for the normalized T is proportional to 1 over CT. So this is relating a coefficient of a 2-point function to the coefficient of a 3-point function, where the precise normalization is some number which depends on your convention, which can be worked out in the exercise. Analogously, you can similarly show that the 3-point function coefficient involving the unit normalized current is proportional to another number called Cj, which is the coefficient of the canonically normalized flavor current. And so this is some relation which only holds for conserved currents. So like if this third operator was just some generic operator, then first of all, we wouldn't have any canonical definition. But we certainly wouldn't know any relationship between 3-point functions and 2-point functions in this way. And so this will actually end up being very useful, because this CT and CJ, these kind of count the number of degrees of freedom of a theory. So to give an example, like if you have like a gauge theory in 4 dimensions, then with like rank n, then CT ends up being proportional to n squared. And similarly, if you have an ON model, then it's proportional to n, etc. And so CT in some sense is kind of like one of the most simple defining features of a quantum field theory, or in particular a conformal field theory. And this shows how CT is related to CFT data, which I define to be the lambdas and the deltas. And so this will be useful once we start, bootstrapping theories, and we want to put like CT as an input, or alternatively, we want to bound to CT. CT can also be measured experimentally in condensed matter systems. So like, there's some nice papers by Sachdev where he shows that like at 0 temperature, there are certain, aspects of condensed matter systems that can be measured that are actually related to the values of CT and CJ. I forget exactly what they are. But I can send a reference to the paper that discusses this. Okay, great. So the next thing we're going to discuss is the operator product expansion. And so this is another very non-trivial fact, which we learned by studying conformal field theory with a quantization. Okay, I think CT and CJ are related to things called transport coefficients, if I recall correctly. Yeah, so I think it's transport coefficients at 0 temperature in a second order phase transition are related to CT and CJ. And so if you like compute these things using bootstrap, then you get predictions for these coefficients in experimental systems.
CJ is just conductivity.
For instance. But CT also has some relation. Maybe heat transport. Okay, so the last application of radial quantization we're going to discuss is something called the operator product expansion. And this is a super important property. Although we're only talking about important properties. Okay, so let's consider 2 operators in some sphere. So this is some sphere. We're going to consider 2 operators, one at x1, one at x2. So this is the first operator, here's the second operator. And so let's give these things some kind of index, A and B, because they can be spinning operators in general. And so due to the state operator correspondence, we know that these operators, we should be able to write them in terms of states that live on the surface of this sphere. So in particular, we can take this operator. So the first one, let's label with an I, the second one with a J. So we can take this operator at point x1, and we can take this other operator at point x2. And when we act on the vacuum, this should be written in terms of some state, psi AB. This just follows from the state operator correspondence. Now, what are the possible states that we have in a conformal field theory? So we know that all states are either primaries or descendants. That's the complete list of states. And so this generic state must be written as some sum, it will actually be an infinite sum of primaries and descendants. So descendants, though, are also related to primaries by the conformal algebra. So we know that given a primary, we can act with various derivatives in order to get a descendant. And so if we want to write everything just in terms of primaries, we can put in some differential operators, I'm not going to define yet, but it has to have all the relevant indices.
just by construction. It has to depend on the position of the two operators, and there'll be various derivatives. And this thing will act on all the operators, and then we sum over all the operators in the theory, which is infinite operators in general. Because as discussed before, the Hilbert space is infinite. And so the point of the C is basically to generate all the descendants acting on these primary operators OK. Now, any relativistic quantum field theory has an OPE. But in a standard relativistic quantum field theory, this OPE is an asymptotic series. So it doesn't converge for any finite radius. What's special about a CFT is that because we can write operators in terms of states, there's a mathematical theorem that any Hilbert space, that any state in a Hilbert space can be written as a convergent sum of other states in the Hilbert space. And so if this was our original state, and if we wrote it in terms of these other states, then this sum must be convergent. And in particular, it converges within this sphere. And this is what's special about CFT.
Because it's kind of related to the question I was asking before. Because kind of what if Hamiltonian is time dependent? Why would it spoil the convergence in the Hilbert space?
Okay, I haven't thought carefully about this time-dependent Hamiltonian issue.
Right.
I'm pretty sure that generic quantum field theories do not have a convergent OPE. Maybe there is some weird redefinition you could do of various quantities such that in terms of these weird quantities, it would be convergent, although I'm somewhat skeptical.
Because I remember in one of the bootstrap meetings, I heard like 2 hours rambling by Zamolodchikov, where he was saying he's not sure, but his gut feeling is that it's convergent in always. And there's the gist of the argument was exactly this.
Well, okay. So the most careful statement is that in a CFT, you can prove that the OPE is convergent.
Right, yeah.
Now, in a non-CFT, it could be convergent. I'm not saying it's proven that it's non-convergent. It's just not guaranteed that it's convergent. And so it's conceivable that maybe Zamolodchikov has some genius proof that in fact it's convergent.
But he didn't have a proof, but basically he was saying all what he was saying during these 2 hours that he doesn't see difference. But it's because
Zamolodchikov sees many things that I don't see.
Right. Yeah.
So it's possible that he sees that. But as a humble man,
you can use the same argument that if you write down the vector as the sum of other vectors in the
right, yeah, that's what we were saying.
And we
but we're using the state operator correspondence. So look, this connects to what Sergey said before. Is that if you could write down some weird state operator correspondence, even for a non-conformal theory, albeit with some weird time-dependent Hamiltonian, then maybe you could try to make some analog of this argument. Because the key thing we used here was just the state operator correspondence. Once you have the state operator correspondence, indeed, it's just a trivial fact about linear algebra that states of the Hilbert space are convergent sums of other states. But the key thing about conformal symmetry was the state operator correspondence. Okay, so this fact is extremely important because this says that given products of 2 operators, you can write it as 1 operator, albeit an infinite sum of 1 operator. And so what that means is that any correlation function of n operators can be reduced to a correlation function of 2 operators by just repeatedly acting with the OPE. And because the correlation function of 2 operators in a CFT is completely fixed, this means that conformal symmetry fixes correlation functions of n operators. Because all you do is you keep acting with the OPE to reduce the n operator to the 2 operator, and that's fixed by conformal symmetry. So this is an extremely powerful fact, which I do not think necessarily holds for non-conformal theories. Now, maybe there's some weird case where maybe it holds, but at least generically, it certainly does not hold for non-conformal theories. I mean, like if you're studying like a 3-point function for some random, field theory, and you're using LSC to relate that to some amplitude, then certainly like looking at an amplitude of like a 5-point amplitude would be very non-trivial, and there wouldn't be any obvious way of relating that to an amplitude like a 2-point amplitude, 3-point amplitude.
And just so that I'm following, so on the left-hand side, these operators are descendant operators.
No, okay. So here are 2 primaries.
Oh, they're also primary.
Yeah. So all operators are primaries unless I specify otherwise.
Okay.
Yeah. So these are primaries. This is some state, generic state, and I'm saying a generic state is written as a sum first of both primaries and descendants, but then to get rid of descendants, I put in this differential operator, which relates primaries to descendants, and thus this O is also a primary. So at the end of the day is 2 primaries be written as 1 primary.
Acting on this with vacuum.
Sorry?
You have the vacuum state on the right.
Thank you. Great. Okay, so let's give some applications of this OPE. So first of all, let's apply it to a 3-point function. So say we have a 3-point function, again, of 2 scalars and some spin L operator, which is our nice standard example. So you can take the OPE. I should also, I forgot to include something very important. There is also a coefficient lambda here, which has the same labels I, j, k. So the point is that this C, I, j, k is something which is fixed by symmetry, whereas this lambda is not fixed by symmetry. It's a number, And so this is something which is dynamical, which you have to compute. And so what I'm about to tell you is that this lambda is the exact same lambda that shows up in the 3-point function. This is why we call these lambdas OPE coefficients. So how do we see that? Well, like say you want to pick out a specific operator OK. So what you can do here is you can multiply both sides by OK, and then you can take the correlation function. So here I multiplied this by OK, I'm taking the correlation function. And in the previous lecture, we learned that 2-point functions of operators, say with delta and delta prime, these are basically orthogonal. That it just equals, the Kronecker delta, delta, delta prime, divided by some position dependence. And so when I take the correlation function multiplied by OK on both sides, this picks out a specific operator here, and it picks out a specific OP coefficient. And so this is just stating that the 3-point function is proportional to this non-trivial number lambda, which is the thing we defined in the previous lecture. And so
can I ask another question? So suppose I was not working with the CFT, but some general QFT.
Yeah.
There also I can define these operators, these primary operators, right? Because they're like eigenvalues.
Okay, first of all, you wouldn't have the concept of primary and descendant, because that's something which follows from conformal symmetry. I mean, you certainly have operators, but they wouldn't be organized in conformal multiples.
I cannot just construct some operator which is an eigenvalue of those two quantities that you defined. One was the dilation and the other.
No, but the thing is that if you don't have conformal symmetry, like you wouldn't have things which are simultaneously diagonalizable in terms of the generator. Yeah. So in fact, this is something. So like when people study like systems on the lattice, when they try to find evidence for conformal symmetry, one of the evidences they find is they look at various operators and they try to see that they are spaced by integers. Because that kind of suggests that there's conformal symmetry emergent at the second order phase transition they're trying to tune to. So there's some nice recent papers by Yin Chen He at Perimeter where this is precisely how he tries to argue that he is finding conformality in the specific lattice system he's looking at. So this is kind of one of the smoking guns of conformality, is that you have this evidence, when looking at your spectrum of states or operators. Okay, so we just reviewed why in the 3-point function, which is proportional to lambda, why that lambda is the same lambda that shows up here. Just by taking the correlation of both sides. So now let's apply the OBE to the 4-point function. So let's consider the 4-point function of scalars, which all have the same scaling dimension, just for simplicity. So we can take the OBE twice. First on these two guys, and then on these two guys. And this is going to give a sum over all the various operators in the theory, labeled by delta and L, all the various primaries. And then you're going to have this coefficient lambda twice, because you took the OBE twice. And then you're going to have your usual function of u and v. And so in the previous lecture, we showed that just on general grounds, you can always write a 4-point function by factoring out some position dependence. So this is just a kinematic fact in the previous lecture. The non-trivial thing we're showing now is that this function of u and v in particular can be written as a sum over all the primaries of the OP coefficient squared times the function of u and v. And so this is kind of a more detailed description of what the 4-point function looks like. And so we still haven't computed the 4-point function. But what's non-trivial is that this g of u and v is completely fixed by conformal symmetry. So this is what's called the conformal block. Because this g, u, and v can just be computed from these c's. Because all you do is you take the OPE twice, and you're going to get some like double sum of these c's times a 2-point function, and the 2-point function is always trivial in a CFT, and that's why this thing is just a completely kinematic quantity. And so because this is completely kinematic, this means that the 4-point function is entirely fixed in terms of two sets of numbers. The lambdas, called OP coefficients, and the deltas of the various primaries, the scaling dimensions. And so this is what's called the CFT data. So these two labels are kind of the heroes of our story, which is that if you could compute deltas and lambdas for all primaries, then you've learned everything about the local properties of a CFT. Now, of course, there's also non-local properties like Wilson loops, Wilson lines, but we're not talking about that in this lecture. For local guys, which is how you study like critical exponents and condensed matter, you only need to determine lambdas and deltas. And this will also teach you everything about correlation functions. Because you can also take higher point functions and take the OBE and get an analogous formula like this. I mean, it won't be a function of just u and v, there'll be more labels, so you have more positions, but it will always just be written in terms of some combination of lambdas and deltas. Okay, so the last thing we're going to do in today's lecture is we're going to discuss, practically speaking, how do you compute this conformal block? Because this is just some kinematic things. So it should be completely fixed by conformal symmetry in terms of delta and spin. It's not something, for which you need to know, any kind of like dynamical property of the system. And conformal blocks are kind of like the kind of basic input to the conformal bootstrap. So it's kind of like the one thing where it's good to kind of know how to compute them, even if at this point there's already like code online which can compute them very efficiently for you. But it's good to have some intuition. So the first way you could compute it, as I just mentioned, is that you could just use this definition of the OPE and write this conformal block as some kind of infinite sum of pairs of these C's, where the C's themselves you could work out by relating to the 3-point function. Now you could do this, but it's very tedious, and it's not the most efficient way of computing the conformal block. But like if you do that tedious exercise, and then you take the limit where u and v are small, then you find that, so this is just some general scaling. So the conformal block is going to scale, like scaling dimension minus spin over 2 times 1 minus the spin. Then there's some normalization depending on your conventions. So this is kind of one thing you learn from that tedious exercise. But let's try to think of a more intelligent way of computing the conformal block. So for instance, let's start with our 4-point function. So here's our two scalar operators, one at x1, one at x2. And now let's insert a complete set of states. It's kind of a standard thing we do in quantum mechanics. It's kind of the standard quantum mechanics trick. So the complete set of states here is summing over all the descendants of the primary. So the primary is labeled by delta and spin, and then the descendants are going to be labeled by m and s, where m is basically delta plus m, and then s is going to be the spin of the descendant. And so we put in this complete set of states. So delta plus m for this descendant, because we're talking about a block for a primary with dimension delta and spin m. So this is the spin of the descendant, the dimension, which is delta plus m. We put in this thing again, because we're doing the complete set of states. And then we have the other operators in our 4-point function. And then we want to normalize by the descendant. Great. So the spin of the descendant, of course, is related to which descendant you're looking at, so the value of m, as well as the spin of the primary. So it can't just be any spin. So one thing we learned from this is that just comparing to the definition of the conformal block here, the conformal block is basically this quantity just multiplying by this position dependence. So if we can compute this quantity, which is we've now written in terms of an infinite sum of 3-point functions, then we have computed the conformal block. And so that's kind of the advantage of putting in this complete set of states, that instead of having a 4-point function, we now have an infinite set of 3-point functions. So one thing we already learned from this representation is that you might remember from the first lecture, we discussed how the fact that in a 4-point function you can permute these operators, this gives constraints on g of u and v. So remember there was 2 constraints. These were called crossing constraints. So one of the constraints from that previous lecture is that g of u and v is the same thing as g of u over v and g of 1 over v. So there was this, and then there's a second crossing constraint. So this first crossing constraint, you can automatically satisfy it on the level of this way of writing the 4-point function by just demanding that the spins of these 3-point functions are even. So if you just impose this constraint, you can see that this isn't saying anything non-trivial about the full 4-point function. It's just saying that all the primaries that appear in this sum must have even spin. And so this is something which is special to having identical scalar 4-point functions. So in this specific case, L must be even. So you must have even spin operators appear. And so this is why this crossing equation is a bit trivial. It's not giving any non-trivial constraint on the full 4-point function. It's just saying something about all the specific primaries. Now there's another crossing constraint, g of uv equals g of vu. This guy is going to be more non-trivial. So this you can't satisfy just by demanding some property of the specific primaries. But this one you can, and that's something we've already done. Okay, so we're going to leave this on the board because we're going to use it in a moment. But for a moment, we're going to discuss a different way of computing conformal blocks. And this is using something called the conformal Casimir.
Sorry, here you're considering 4-point functions with the same delta, or?
Yeah, so I'm talking about 4-point functions of operators which all have the same delta phi.
And so this logic can be applied for any correlation function, right?
So the fact that the operators that appear in the 4-point function, we call internal operators, the fact that their spins have to be even, this only holds for 4-point function of scalar operators with the same scaling dimension. So later on in the class, we will talk about 4-point functions of scalars with different scaling dimensions, and then you no longer have this constraint. But we're just talking about like the simplest example.
So you mean that this GUV equals G over UV times 1 over V is not such like is that
Well, I mean,
satisfied?
you always have these constraints, just they're satisfied in different ways.
Oh.
Yeah, so when you have a non-trivial 4-point function, then it will become a non-trivial Gaussian equation. It won't just be satisfied just by demanding the spin theory. Okay, so the way we're going to discuss computing the conformal block is using the quadratic Casimir. So in general, like whenever you want to compute eigenfunctions with a certain symmetry, usually the best way of doing that is you take the generators of that symmetry group, you square it to get a Casimir, and then you find the eigenvalues of that Casimir. So this is kind of a general strategy, and we can apply it to the conformal group, which remember, is just isomorphic to SOD plus 1, comma 1, as we discussed in the previous lecture. So let's write the generators of SOD plus 1, comma 1 as LAB. So this LAB can be written in terms of the DPKM that we've been discussing. And so the quadratic Casimir is just the square of these generators, usually written with a half. So this is defined as the quadratic Casimir. And so one of the properties of a Casimir is that when you act on a state in your system, it just gives a number. That's kind of the defining property of a Casimir. Right, so this is a certain number you can find in the notes. It depends on the scaling dimension and the state. And so then the strategy, though, is that these L's, they can also be written in the differential representation. So remember in the previous lecture, we discussed how the generators P, K, D, and M can be written as like derivatives. And so that means these L's can also be written in terms of derivatives. And so we can think of this L, written as, some differential operator, so it depends on derivatives and positions. So we can have this L acting on, say, 5x1 and 5x2. And so you just act with L on these operators using the conformal algebra. And this ends up giving, so first of all, just think of this as the abstract generator. And then once it acts on the operators, we can now think of it as acting as some kind of differential operator, which I'll denote by kind of curly L. So there's going to be a differential operator acting at point 1, and then also some differential operator acting on point 2. 5x1, 5x2. And so you can work out precisely what this differential operator is. And then the idea is that you act with this differential operator on just 2 of the points in the 4-point function. You leave the other 2 points alone, and that gives you an eigenvalue equation. So on one side you have this little c, which has an explicit definition. The other side you have some, derivatives in terms of the 4 positions. In particular, you can write those derivatives just in terms of u and v, because that's kind of, required by conformal symmetry. And so at the end of the day, you have some eigenvalue equation, and you want to find the eigenfunctions, and then those can be the conformal blocks. So in principle, this works in any dimension, but people only actually know how to solve this eigenvalue equation in even dimensions exactly. So just to give you an example, so in 2D, which in condensed matter would be 1 plus 1 dimensions, if you solve this eigenvalue equation, it's easiest to write this in terms of some auxiliary variable z. So you define this to be u equals 1 minus z, u equals z bar, v equals 1 minus z, 1 minus z bar. And so in terms of these variables related to u and v, this thing is proportional to k delta plus L, k delta minus L, this is function of z bar, I'm going to define these k's in a moment, plus the complex conjugate. And so these k's are just hypergeometric functions. So, I remember when I first started doing physics and I encountered a hypergeometric function, I thought it was like this horrible thing. And now when I see a hypergeometric function, I'm very happy because I'm like, oh wow, it's just a simple thing. So it shows how your kind of approach to hypergeometric functions changes. So this is actually a very simple answer. So conformal block, at least. Yes.
What is the indices of this curly L? The first indices.
This is just referring to. So A and B refer to which generators. And so you're going to have, I was a little bit not careful. So you're acting with the Casimir, so you actually have two L's. So I was saying how one L acts, but to get your differential equation, you're going to act with the second L and contract these things. And so these indices are just writing down the various generators. And so you're gonna get this times itself, and that's gonna be a differential operator acting on the conformal block. And so all these indices are gonna be summed. And so another way is that it's gonna be a product of combinations of D with D, D with K, P with K, etc. All these things are written as various derivatives, you simplify it, and you get some differential operator acting on the conformal block, and then you solve that eigenvalue equation. And so the solution to that eigenvalue equation is given explicitly here in terms of these hypergeometric functions, and so it's a very, very easy solution. And so this is in 2D, and in higher even dimensions, it actually looks very similar. So it's always basically just like a product of hypergeometric functions, maybe dressed with some extra factors of z and z bar. But unfortunately, we only have these easy solutions precisely when D is even. On the other hand, though, this differential equation, which you can derive using the quadratic Casimir, in the differential equation you get, D is just a parameter. So then in principle, there's a solution for any value of D, even for any real value of D even. Like you could look at D equals 2.6. It's just that we only have a simple solution when D is even. So if you want to get an explicit solution for other D, there's no closed form solution, but you can compute it in a expansion. And it turns out that expansion is actually the most useful in general, even in even dimensions.
Can you elaborate on that? Because in even D, well, we just call this solution hypergeometric function. So we just call it some function odd D. Is there a sense in which that solution is more complicated, really?
Well, okay, there is no special function with simple properties.
Yeah, but if we just call, let's introduce a new special function.
Sure, but I'm saying, yeah, but that special function doesn't have simple properties.
Yeah, so there is definite sense
Yeah, I
in
mean,
which
yeah,
the solution is more complicated.
Yeah, you can always call a function a name.
Right.
It's just that hypergeometric functions existed before conformal blocks. And hypergeometric functions are very simple properties. We know a lot about them, and it turns out that these known special functions appear in conformal blocks. For other blocks, you would have to find some new function, which is called the conformal block function, let's say. And that's a new function which we now have to study, and we have to compute what it is in some kind of expansion. And so the last thing I'm going to talk about is this expansion, which is called the Zamolodchikov recursion relation. So this is something which was first worked out actually in 2 dimensions by Zamolodchikov for 2-dimensional Virasoro blocks, but it turns out that the basic idea works in any dimension, even for blocks under this global conformal group. So we don't have to specify the 2D. So we're only talking about D bigger than 2.
But a quick question.
Yes.
So when you use this procedure, like you have this expansion where you introduce this complete set of states, right? So you just multiply once on CAB, and after that represents the CAB by these operators.
Well, okay, so
and after that you get a simple differential equation.
Okay, so this complete set of states, I don't have to use this for the quadratic Casimir argument. The quadratic Casimir argument is that you just have 4 operators at 4 different points, and you act with the quadratic Casimir, which is acting on 2 of those points. And the quadratic Casimir, by definition, has to equal a number, which is some function of delta n. And so the statement is that you have differential equation on one side equals number on the other side, and then you're just solving that eigenvalue equation. So I didn't have to use anything about the set of states. The set of states I used, first of all, to motivate that you could solve this crossing equation just by demanding the spins are even.
Okay.
And I'm about to use this thing again to describe Zamolodchikov's recursion relation. But I didn't have to use that for the eigenvalue equation.
So I have a more general question. So
Yeah.
when you write down these OPEs in D equal to 2,
Yeah.
they have a nice interpretation as anions and fusion and all that stuff, right?
Yeah.
But what about, but you're saying you're staying away from D equal to 2.
Yeah,
anyway.
so yeah, so
what is there a similar interpretation?
No. Not as far as I know. I mean, like the whole anion story is very special to 2D. So yeah, so like in 2D, you have this relation between topological field theories in 3D and kind of conformal field theories in 2D, but that's special. I don't know of a similar relationship in higher dimension.
Should we act on these 2 points, like 2-point function, not 2-point function, but 2 operators? It's like we only act on at 1 point, right? So it doesn't matter how many.
But these differential operators are acting at 2 points. So that's basically what I was trying to write here. Is that you have the quadratic Casimir acting at 2 points, 1 and 2. The reason why we choose to act at 2 points is because we know that the function we're trying to fix is a function of 2 variables. So that's why it makes sense to write down a Casimir acting on 2 points. And in principle, we could have also written down a Casimir that acted on all 4 points, but that just wouldn't be necessary.
So it will be just a sum of 4, or it will be something?
You say if you would have written down the Casimir acting on all 4 points? Well, I mean, you could have something like quarter Casimir, which could have acted on all 4 points, and like the solution to that would have to be the same conformal block, by consistency. But we're just trying to write down the simplest differential equation. So the simplest differential equation is to consider the quadratic Casimir, which is the simplest Casimir, and that acts on 2 points.
It doesn't matter which 2 points you choose.
It doesn't matter which 2 points. Yeah. Well, I mean, depending which 2 points you choose, I mean, the details will be a little bit different.
Yeah.
But you're going to get the same conformal block. It's related by conformal symmetry. Okay, so let's go back to when we were writing this thing to be proportional to our conformal block. So the first thing we're going to do is let's write this equation in terms of cylindrical operators. So that means instead of having x1, x2, x3, x4, we write it in terms of r and eta. And in particular, we are going to fix our points using conformal transformations as follows. So we can always use conformal transformations we start off with 4 points, and we know that at the end of the day you get a function of just 2 variables. And so we must always be able to fix these 4 points, which are in principle d times 4 labels, in terms of just 2 labels. That was kind of advertised in the first lecture, although not proven. So here, I guess we're going to kind of sketch the proof, and then we're also going to use this proof. And so the idea is that, first of all, you can always use a special conformal transformation to make one of the points go to infinity. You can use you can use translations to move another point to 0, and then you can use dilations basically to get rid of all the other dependents except for 2 points. So maybe let's first draw that picture. So the idea is that one of the points has been sent off to infinity using special conformal transformation. Another point has been fixed to the origin using a translation. Then we use a rotation to fix another point just to lie right here, at the value 1. And then our last point, is just some generic point, somewhere here. But we can use dilations so that this is just a unit vector. So then at the end of the day, if we define this to be z, we have shown that we can write all our 4D variables just in terms of 2 variables, or basically 1 complex variable. So it's for z equals a plus ib, and so z is basically this complex vector, which has height a and length. And then this z and c bar are then related to u and v, as I wrote up there. And so this is kind of reviewing the fact that the 4-point function is a function of 2 labels, not 4D labels.
A squared plus b squared is equal to 1.
Yeah. So I use dilations so that this x2 is a unit vector. Yeah. Okay. So this is called choosing a conformal frame. So now instead of choosing this conformal frame, I could choose another conformal frame written here, also by using dilations, rotations, etc. So in this conformal frame, x4 is at -1, x3 is at +1. This is the origin.
Yeah, didn't you use dilations to put third point to 1? I don't think you have freedom to use dilations to
It's equivalent, but
Sorry, let me make sure I'm
otherwise we need to specify what the magnitude of the x3.
Okay, so I put x4 to infinity. I translated this one to the origin.
You use special conformal.
I rotated x3 here. I used dilations so that x3 has a unit norm.
x3.
X3 has 1, right?
Yeah, x3 has 1, not x4.
X2 is a infinity.
And then sorry. So x2 does not have unit norm. Yeah, of course it does have unit norm.
Yes,
if it had unit norm, there would only be 1 label. Yes.
Right,
Sorry,
yes.
I misspoke. Yeah. So x2 depends on 2 variables, a and b. A squared plus b squared is not. Thanks for correcting that. Okay, so now we're going to choose a different conformal frame. So now x1 is here, x2 is there, so they're along the same line, and so I call this radius rho. And so instead of the variable being complex z, in this case, now the variable is complex rho. And so the usefulness of this frame is that this is kind of conducive to talking about cylinder coordinates. So let's define r to be the magnitude of this complex rho. So this is the length of that rho. So then I can now write this equation in terms of cylinder coordinates. And so if you're now, okay, so I write x1 and x2 and x3 and x4 in terms of this conformal frame. And when I do that, I can just take out a factor of r to the delta plus m, where you get delta plus m because you had these internal states which had scaling dimension delta plus m. And you basically have the dilation operator acting on the state, and that's what gives you r to the delta plus m.
Sorry, and you're still in general dimensions, right? Generic dimensions.
So general dimension bigger than 2. So I'm working in general dimension bigger than 2. And so I can take out the radius dependence of these operators, and so now they're all at radius 1, although they still depend on a general angle. Similarly for these guys. So these things are all at radius 1, they just depend on various angles. And the important conceptual fact is that this gives a factor of r to the delta plus n. The remaining 3-point functions, which no longer depend on r, they only depend on angles, and so you can compute these things in terms of some function, which is called a Gegenbauer polynomial, which is basically a generalization of spherical harmonics to the case of general dimension. But I mean, that's not so important, you know, that's in the lecture notes, the precise quantity. The point, just conceptual point, is that this thing can just be computed explicitly, and it's not going to depend on r because we've already factored out r. And so right now what we have is that we have conformal blocks are written as a sum of r, where r is getting bigger. So r starts as r to the delta, you know, because m starts at 0, and then you have infinite descendants, you know, m equals 1, 2, 3, 4, 5, and so it's written as some expansion in r. And so this is kind of like a nice natural expansion of conformal blocks in terms of this r. So the next thing we do is, the way we get a recursion relation is that we note that there are certain values of scaling dimensions delta below the unitary bound. So for physical operators, delta is always above the unitary bound. But mathematically, you can always consider delta below the unitary bound, and there are specific values of delta below the unitary bound where you would get negative norm states. So that means this quantity would become 0. And so when you get a negative norm state, that basically means that what would have been a descendant now becomes a primary. So basically another way of saying that is that there is a special value of delta such that you can write your conformal block in terms
norm or null state.
Sorry, it becomes a null state.
Not negative norm. Pure norm.
0 norm.
Yeah.
0 norm. Yeah. So the bottom becomes 0.
Yeah.
So it becomes a null state. And so when you get a null state, what used to be a descendant becomes a primary. Now, of course, this only happens for negative delta, so this doesn't apply to physical CFTs. But right now, we're just trying to get some mathematical equation which will allow us to get a recursion relation for these blocks. And so because we know that there are negative values of delta where this becomes a primary, which itself must have a block expansion.
Not necessarily negative, right? Just below the unitary.
Below the unitary bound. I mean, generically it would be negative. Okay, so let's write the block as a function of this r as well as eta, which is basically this angle. And so based on the existence of these null states, okay, so this is just some coefficient. This delta im is the value of these null states, which I told you exist below unitarity. And this must multiply a block itself at delta im. For here, we are summing over all these special values of delta.
But you should argue that this conformal block as a function of delta is an analytic function of delta.
Well, no, I mean, I don't have to argue that because this statement just comes from the fact that you have these null states. I don't have to say anything else. So like the fact that there are null states for special values of delta, if you believe that to be the case, which you can check based on the explicit formula for blocks that's written in state terms of these Cs, then that immediately implies that in this sum, like this state that used to be a descendant is now a primary, which means it itself has a conformal block expansion. And so what you're saying is that there is a pole corresponding to that null state, because there's clearly a pole there, because when you have a null state, this is 0, so this is a pole.
Yes.
So what you're saying is that there are poles in delta, and at those poles, you have another conformal block of the dimension, which is like basically the residue of that pole.
Yeah, but I'm just arguing that there is no some non-perturbative factor that has essential singularity at infinity.
Okay, so there's also essential singularity infinity. That's what I've written here. The essential singularity at infinity, you can basically prove by just solving the eigenvalue equation in the limit where r goes to infinity. Because in that limit, it's kind of easy to solve the eigenvalue equation in any dimension. It simplifies. So this specific guy, which is the essential singularity, this is just some known function. And this thing can be computed very easily by looking at the eigenvalue equation in this limit as delta goes to infinity. Sorry, so this is
R and
yeah, so this is a function of r and eta.
So it's again some hypergeometric functions.
It's yeah, well, not hypergeometric function, it's actually Paul Hammer's. But okay, but anyway, so this is some special function which you can solve from the eigenvalue equation. This is the essential singularity. Other than the essential singularity, the other singularity are poles which occur when some of these descendants become primaries at these weird values of delta below the unitary. And so this gives a recursion relation, because you have a block is written in terms of other blocks. The precise value of these residues can be worked out basically experimentally. That's how people first computed them. You basically just took your expression for a conformal block, and you looked at the residue of these various poles, and you computed what these values were. You looked at many different values.
How do you know the residue?
Sorry?
How do you know the residue?
Well, because look, you can always compute conformal blocks laboriously, just by taking those C's and taking the sum. So like you always have a way of computing conformal blocks. That's just like a very tedious way. What I'm giving you is a more efficient way in terms of recursion relation. And so the idea is that you use the tedious way in order to find the values of these residues. And after you know the values of these residues, then in the future, you can then compute this block in this expansion over R. There should also be a factor of R here.
So this coefficient SIM depends only on IM.
Yes, this only depends on, so this is a coefficient only depends on IM. It does not depend on delta. So all the delta dependence is written. So
I thought it's the residue of G delta L.
Sorry?
It's the residue of G delta L
Yes.
at delta equals delta.
Yeah, but the residue also includes a conformal block itself. So the residue is this times that.
Yes.
Then how do I know that the residue is only CIM just depends on, it doesn't depend on.
Well, okay, but this is kind of guaranteed by conformal invariance, because the fact that this null state becomes a primary means it must be expanded in terms of a conformal block. So it must be a conformal block just times some number. So this is the number which multiplies it, but then conformal symmetry says the position dependence has to be that of a conformal block. So that's the fact that this is a null state where a descendant became a primary. Okay, so we have this recursion relation, and we combine this with the fact that generically conformal blocks are proportional to R to the delta plus n with the sum over n. So that's the second important ingredient. Because this means that we can define now an auxiliary function, h delta L of R and eta. This thing is just defined by just stripping out some R dependence. I'll ignore this overall factor for simplicity. So we strip out the R dependence from the conformal block, because we know that it has that R dependence from the argument over there. And then this recursion relation, in terms of this H, is now written in a very nice way. So it's H delta L of R and eta equals H infinity, which is just defined in terms of the G infinity, which is a function of R and eta. Because this thing basically had an essential singularity of R to the delta. It's part of its definition. So like this thing is proportional to R to the delta, as you can see from that definition over there. Plus, the same sum over here, the sum over this I, and then like M has to take certain values, which are given by these BI's, which are given in the lecture notes. You have these coefficients that don't depend on delta, these C's. You have the poles at all the values of these special null states. You have R to the delta, because that's how H is related to G, and then times the H block of these descendants that have become primaries. And now this is a recursion relation which can be computed perturbatively in R. So just to quick, the argument is a little bit messy, so let's just go over it again. There's basically two steps. First of all, we know that conformal blocks in general are an expansion in R, which scales with delta. And that we learned by choosing this specific conformal frame and using cylindrical operators and taking the dilation operator acting on each of these descendants. The second step we used is we make the experimental fact, which can be checked, that there are special values of delta below the unitarity bound where you have null states. And when you have a null state, that breaks up the conformal multiplet. And so what used to be one conformal multiplet now becomes multiple conformal multiplets with multiple primaries, where the new primaries correspond to these descendants. That fact implies that at the pole corresponding to these special values of delta, you must be able to write the original block in terms of the blocks of those descendants that have become primaries. But then we just rescale G by R to the delta, because we know that R to the delta dependence, and then that gives a recursion relation, which is naturally written as an expansion in R. And then you can just solve this recursion relation perturbatively in R. And this works for any dimension D. So in particular, these C's are a function of spacetime dimension D. And like this B is like the specific set of descendants that become null states. That table of those values is given in the lecture notes. That also depends on D. And you can do this for any spacetime dimension D. So in particular, you can also do it for even D. In that case, it becomes a little bit subtle, because then it turns out that these C's themselves have poles, such that you then have double poles. So this sort of becomes a bit trickier in even D, kind of ironically.
But you said C doesn't depend on delta M. It only depends on delta I and delta M.
Well, no, what I'm saying is that it gets, like, these C's basically diverge for special spacetime dimensions D. And so because they diverge, that means like this formula is not totally correct. And the reason why it's diverging, sorry?
It is posed in delta.
No, this thing has, as a function of D, has poles when D becomes even.
But then it's not a double pole, right? So pole at delta equals delta IM.
No, but I mean, but the fact that you have a divergence just means that your formalism is broken down. And when your formalism is broken down, this means that you have to write a new expansion. It basically means that like your assumption that there were single poles was wrong. In fact, in even dimensions, there's actually double poles. And so you have to write down an analogous recursion relation which has both double poles and single poles. So that's also been written down, but like for simplicity, we're just going to talk about the case where D is not an even value, and then this formula holds.
So roughly speaking, unitarity bound works in this strange situation.
Same when D is even?
In even dimensions.
No.
Roughly speaking, instead of changing the sign of these norms, just bounce back. That's what you want to say.
Why do you say that?
Because of, roughly speaking, what is the denominator? The norm of this guy. Right?
Yes.
So roughly speaking, we have double poles there. It means that goes 1 over D minus D prime squared.
You're saying like, how from this formula do you have an intuition about the fact that there are double poles?
Yes.
To be honest, I never thought about that before. I guess it's just implying maybe, I guess like these 3-point function factors must have poles themselves. You know, because I guess that's the only way from this formula you can get a double pole. Yeah, I mean, I don't have a physical intuition about why you have double poles in even dimensions.
You said that the molecular origin is just about D equal 2. So how comes in D equal 2 there are double poles to start with, right? Yes.
Well, because it's an even dimension.
Right, yeah.
Yes.
So that means that should be very different from his argument, right?
No, I mean, the general idea of the sum logic of recursion relation.
Discuss determinants.
Yeah, I mean, like, okay, so the general idea of the sum logic of recursion relation is just that there are null states below unitarity, and that's what gives you a recursion relation. And so we're just applying that in general D. It was first done in 2D, where the property is slightly different, but it's the same general idea. That's why we call it sum logic of recursion relation. Okay, so this concludes this lecture, exactly on time. I leave a couple minutes for questions.
Yeah, so again, are there any elegant results for the entanglement and things like that for D greater than 2? Because I know for D equal to there are these famous results, right? For that there, if you look at measure the,
I mean,
you calculate.
you can compute entanglement entropries in D bigger than 2. It's just harder. So it's like in 2D you have kind of special relations that make computing entanglement entropy particularly simple.
But it's not related to one of these, like in.
No, okay. So the reason why 2D is simpler is because the conformal group is bigger. So the conformal group is what's called the Virasoro group, which has infinite generators. The conformal group I'm talking about here is called the global conformal group. That's the thing that's defined in general D, and that has a finite number of generators. You know, it's just P, K, D, and M. In 2D, you have infinite generators. And so, look, in 2D, you can talk about the global conformal group. So in 2D, you would have like, you know, SO3, 1. And so that would be a subgroup of the Virasoro group. And so you can still talk, so like, you know, so many of the results in this class will also apply to 2D, just that 2D you could do better, because you can define the Virasoro group, which is much bigger. And so like, you know, for instance, in 2D, the stress tensor is actually a descendant. It's a descendant of the unit operator. So it's trivial. Whereas in higher D, that's not the case. And that's because in 2D, you have this like bigger conformal group. And so the fact that the stress tensor is kind of trivial, like that leads to a lot of these simplifications. Like, that's like related to the fact that you compute entanglement entropy in a very simple way in 2D. In higher D, life's a little harder.
Thank you.
Great. Okay, so thanks everybody for coming. Next class will be on Monday, and I will send out an email about the various problem sets if you want to do them based on today's lecture. And I will say that starting next week, we will start talking about programming. I mean, it will still be conceptual discussion, so hopefully it doesn't scare anybody away. But it will be programming as applied to conformal field theories, because we'll talk about how to actually use the conformal bootstrap to solve CFTs using this formalism we've set up in the last. Okay.